Hey y'all, Data Guy here. In this video, it's kind of a follow-up to my previous video where I went over, what is data modeling, how can you implement it, and what this video will explore is more about, hey, what are the different types of data models, what are the pros and cons of each of them, and what are the use cases that they're really good for. So I know I touched on a few of these in my initial video, but in this, we're going to go through almost 15 different data models. So you can have a full understanding of the different options available to you for whatever use case you might need. And kicking it off here, we have the relational model. So the relational model is probably what you think of when you think of a database. It organizes your data into table relations with rows and columns, and it's really the foundation of SQL databases. Pros are that it allows complex queries using SQL. You can define these relationships really really rigidly. You support data integrity by having ACID properties, ensuring that, hey, every transaction is going to follow the same steps. And ACID is atomicity, consistency, isolation, and durability. We're not saying all those database guys are tripping. Now, also, normalization, it reduces data redundancy. Everything is really stored in only one place. You don't have multiple sets of the same data other than these primary keys, which can be referenced across tables. So really, really easy, or not really easy, pretty hard to set up. But once you have it all set up, it can be a really defined structure that all of your data will just automatically follow. Cons are that it is rigid. It's really difficult to change the structure of one set. If you want to change one table, you might have to change several downstream that are actually linked to it. And when you get up to a certain size and a certain scale, the performance degradation can be quite significant. It can get really slow for larger databases. So this is really ideal for applications that require complex transactions, banking systems, CRM, ERP systems, where you have a really defined relationship that you want to set, and then you want all your data to be organized in that for easy querying and just easy understanding of the data. And that's a relational data model. Now, second, we have the hierarchical data model. And this will organize your data in what you might think a tree-like structure where every record has a single parent. And the pros of this are, it's an intuitive structure. It can mimic real-world hierarchical relationships, provides really efficient read operations since you have a direct path access to the underlying data. The cons of it, though, are limited flexibility. Each child can only have one parent, so you can't have really complex family tree style structures where you might have some X's and divorcees involved. Complex updates, adding or deleting nodes can be pretty cumbersome once you kind of set up the structure. And then really the use cases it's best suited for are things like organizational file charts, file systems, and XML data structures, where it's just strictly like, hey, you have a folder or folders of files. And it's just, you want to have that really clear, easy relationship, and you don't need that kind of complexity where you have, something can be part of multiple folders. MP3 can't be a television and an electronic, or in a portable electronic in the folder in the hierarchical data model. And so 3, building off of the hierarchical data model, we have the network model. And the network model allows each record to have multiple parent and child records, so it'll really forms a network, as you might guess. This allows for more flexible relationships than a hierarchical model. It provides more efficient data access to the data. The cons are that it can be a more complex structure, more difficult to design and manage. There can be redundant data. There can be data duplication that occurs to this. So it's really ideal for telecommunication networks, which you can kind of see here. We have the network factory and transportation networks, where you might have a pylon that is part of a network of pylons to distribute data passages. Or you have a network. Let's say all the cities in America, they're all connected by the highways. Highways would be connections. A highway can go to multiple cities, can join multiple cities. Kind of think of it like that, and that's where a network model might be useful. Now here we have something that looks similar to the relational model, but actually isn't. And this is the entity relationship model. So this is more used in database design. So it's more about designing, hey, how are these different data tables going to actually interact with each other and live together? It's not as rigid as the relational model because you aren't hard linking it by having this one primary key that has to be common across them. So it simplifies the database design by giving you kind of the entity relationship diagrams and gives you more flexibility where I can change primary keys across. You still have that kind of system, but it's more adaptable, and it also just makes it easier to understand relationships here. So you can have multiple, let's say, warehouse codes that go into code for warehouses, and just kind of an upgraded version of the relational model. This does require translation to a physical schema. So while the kind of high level linkages are here, you'll still have to define, when I say translation of physical schema, you're still going to have to figure out, hey, these IDs. But at the high level, when you're just designing it, you can just kind of say, hey, I know shopping basket, customer, shopping basket, book, all have to relate to each other. And so obviously this can be intricate for really large systems, but it's just a really good starting point for designing databases of any size. So with complex systems, you can just define, hey, I know I want to have this book that is connected to author, publisher, and I know what warehouse it's in. And then you kind of use the relational model to actually define the linkages. Hey, this primary key is going to be used to identify it here. So I like to think it's just really a much more complex, or not complex, but like a starting point for developing, how you're going to connect different databases. Now, next we have the object-oriented model. And while you might think, oh, this just looks the same as a relational model, you're wrong. This is where you're actually going to represent, so there's no difference from relational model here, is that none of these IDs, nothing is directly linking it into the data to this person. Instead, in an object-oriented model, you actually define these relationships. So this person can be a student, he can be a doctor, he can be an engineer. And that relationship is defined here. It's enshrined in code saying, hey, this person is an engineer, so assign them this engineer object that contains all their engineering information. But the person himself doesn't necessarily have to have the engineering ID contained within that object. So this is really good for mimicking real-world objects, which eases conceptualization. It's a much more human-readable way of looking at things. It also allows you to bundle data and operations, so enhances security, reusability. You can define, how people can become engineers, things like that. But as you can imagine, this is just a very simple example. Defining these actual relationships can be quite complex. And as you can imagine, because you don't have those kind of common keys across the different objects, translating this into a relational table can be quite difficult. So this is suitable for systems where real-world modeling is like really crucial for things like simulation software. But in when you need to store lots and lots of data, it might not be the best fit. Now, a slightly more complex version of the object-oriented model that kind of combines a relational database with an object database is the object relational model. Surprise, surprise. And so this, again, combines the features of both, where you have, complex data types and relationships. You can, define, hey, this is how, your child relates to the parent. But you also have the common keys, like OID is in this data table. It's also in this data table. You have keys that are common across all these objects, and that makes it easier for you to actually, say, hey, I know that this ID of this object relates to this version of this object. Because most object relation models, you're going to have, let's say for child generalization, you're going to have 30 objects of different childs of generalization, and having that OID lets you link, hey, number 4 child generalization links to number 4 generalization. It links to number 4 abstract attributes. So you're making sure that you're linking the correct version of each of those objects to their proper versions of the other objects. So this really supports complex data types, relationships. It's adaptable to various application needs. But again, much more intricate to design and manage, and also pretty slow because of just all the added complexity by combining both these types. So this is really ideal for applications that need complex data representation, and that could be something like a geographical information system where you need to say, hey, this city has this longitude, this latitude, has this many people. It's got just all the complexity that you need for actually having a true kind of simulation there. Now, to completely reverse the level of complexity, you also have the flat model. And in a flat model, data is stored in a single 2-dimensional array. It is easy to understand and use. It is really efficient for simple unstructured data where you just need fast access. But obviously, it's just one table in 2 dimensions, so there's no support for like relationships, data integrity. It's not really suitable for any large or complex data sets, but it's good for small, simple data sets. Like let's say I just want to import bulk information around people and their occupation, or configuration settings, things like that. So really good for really small, simple data sets. But if you get more complex, you start having relationships you need to manage between data tables. Obviously, not a really good solution. Now, in a semi-structured data model, this is what things like JSON, XML use. you have kind of a parent-child relationship, but you can also have relationships between the children. So you can see here, this is a bibliography where you have multiple books and papers. Each of these books and papers have an author. The author has a first and last name. And this is really adaptable to changes because as you create the data, you assign it a label of what it is. Data includes tags or markers defining content. So when you add a first name to an author, you define the field under author as first name, and that's an atomic object. Whereas complex objects would be things like a paper that contain linkages to an array of pages, authors, titles, etc. Really good for, if you need to constantly change your data, you just need quick, easy access and you want to change it on the fly. But cons are, as you can look here, it already gets a little squirrely in a pretty simple example. And so this can lead to inconsistent structures. You can have challenges in querying and analyzing this data. And also the storage overhead becomes quite significant because you have to have all these different labels, tags, markers. But it's really well suited for data with a variable structure like web data. So that's why JSON and XML use it. Now, next, we have a document model. And this is used in document-oriented NoSQL databases like Mongo, where each data point is stored as a document, which can have any structure of any field it needs. So even though this is one example of, hey, I have a document that says Jane, last name, address, there could be another document here that only says the first name and the address. It doesn't have last name or hobbies. And so you aren't defined by, hey, every document has to have the same format. They are each individual data points. And so this is really good if you need flexibility, accommodating various diverse data structures. And it also is pretty scalable. You can handle large volumes of data well. So each document is assigned an ID, makes it easier to reference it. The cons of it are complex querying. Querying and indexing can be challenging. There's a lot of systems out there, maybe like Couchbase, like MongoDB, that can actually help you with querying in. They have their own languages for it. But in general, it's just going to make querying more difficult. And there's also potential for data redundancy because, it's not checking, hey, does data already exist? You can easily get duplicate data, but it's really ideal for, things like content management systems, catalogs, keeping track of, user form entries, things like that. Next, here we have the key value model. And in the key value model, data is stored as key value pairs. You might notice a theme with the names of these models and how the data is stored. And so the simplicity here, advantages here are the simplicity of it. Very straightforward model to build and manage. It's got really fast read-write operations. You search for Greg and it gives you Greg's number. You search for an IP address and it gives you the MAC table. Or MAC table number. I actually don't know what that means. But this is really good for really high performance, fast read-write. And then the obvious kind of drawbacks for this is no complex queries. Each key can only have one value, and it's not really suitable for structured data relationships where you want to have multiple objects relate to each other, multiple tables. It's really just good where you just want to store a list of values and whatever their private value is. So good for caching, session storage scenarios where just quick data retrieval. Hey, I want to store the API token that I'm using to connect to this website, and then be able to quickly retrieve that so there's no latency in how I connect to the website. Now, in a graph model or a Levitt model, we're already padding double digits, you have graph structures with nodes, edges, and properties. So you can see here, a person is making a booking for a seat in a section, which is in a row, which is in a cinema. And here you are able to define these relationships called the edges. You have the nodes, which can contain a set of data, or their properties of the node, and it really allows for flexible relationships, really interconnected data, and it has efficient transversal for fast operations, across these complex relationships because you have these relationships already defined. It doesn't have to try and guess. Downsides are that it has, you need to be really thoughtful in your design. This is only really suited for hey, if I have this really defined set of relationships, and it's pretty demanding in terms of compute and storage. So this is really good for things like social networks or recommendation systems or network analysis. We want to see, hey, how does this person relate to other people or things? But again, just requires a lot of compute and kind of thought behind it to actually make it really efficient. Now here we have the dimensional model. And this is kind of honestly similar to the relational model, but it separates measures and facts from dimensions. So what this means is you have dimensions, which are kind of just, they're non numerical values. So like customer name, product name, order date, store name, promotion name. And each dimension, as you can see, is linked to a series of facts. And so these facts are measures. So facts are, going to be things like customer city, customer state. Measures will be obviously, the numerical values here. And so for each, dimension, you have, a fact within that describes it. You have very, very, defined rigid relationships between, hey, this sales order contains these 6 or 5 keys, and these 5 keys link out to these 5 or 4 different tables. And actually 5, because order data is also their own, that contain facts about each aspect of that dimension. So dimensions are described by measures and facts, and this is, the typical is the, scar schema setup, and this enables, it's really optimized for queries. It's optimized for really fast read operations for analytics, and also making it understandable to business users, although I don't know how many business users would actually be able to understand a table like this super easily. Then the cons are, it is very flexible. If you want to, let's say change how your data is stored in the sales order, remove one of these, maybe customers also linked to a series of other tables. It can be really difficult to change that once it's already set up. And it can also lead to redundancy in dimension tables. So, if you have a ton of different dimensions, so in this example, actually, there's no redundancy. But you could have things like, hey, maybe the product also needs to have this store ID on it, and you need to kind of guard against that. Use cases here are, it's really good for BI and data warehousing. If you want to have these really defined relationships, that makes it really easy to query, makes it really easy for a, data warehouse or data analyst to understand. This is a great option. And then the rest of these models that I'm going to talk about are really just types of dimensional models. So you don't also have, so this is a star schemas type where you have, a single fact table that is linked to many different dimensional tables around it. Again, good for querying large data sets, simple to understand, and it's really suitable for, OLAP systems and business reporting. You also have a Snowflake schema model where you can actually have, a central fact table, a central fact table, but then it's linked to dimensional tables that then might be linked to sub-dimensional tables. So they're describing the other dimensions of the properties of the dimension table. So it gives you more complex data, more structure, but again, harder to change, leads to more complex queries, and just also complicates maintenance. And then the kind of final boss of these dimensional models is the multiple dimensional model. And this is where you get 3D with your dimensions. So this is, again, used for OLAP systems, efficient for complex queries where you can have layers upon layers upon layers of dimensional tables. It's pretty challenging to design and maintain, requires significant processing power, but it's good if you have kind of that time sum where you say, hey, I want to look at this data across a series of times. And so it's, again, good for complex analytical tasks and business intelligence because you define all this complexity here. So that part gets hard, but then, once you have it set up, it makes it easier for queries. And those are all the data models that I could find. I hope that, if I missed any, let me know in the comments. I hope you found this video helpful if you are looking to choose, which data model you would like to use. And above all else, have a great rest of your day. Data Guy out.